ranges from -1 to 1, but from -infinity to 1, because this on the left there's no shock front, right? It's just a dilute gas. Okay, and so at the right, this is what is known as the Rankine-Huguenot boundary conditions. But on the left, we use these different boundary conditions, which zero. Okay, so I mean, we just kind of guessed that these are reasonable boundary conditions, and so we have to solve these equations with these boundary conditions. But now this beta exponent is not known. Okay, but then you can just treat it as a, like, you have to solve this with these boundary conditions. So it's like a, I mean, you try to estimate beta so that somehow this is satisfied. Okay, so then from this numerically we solve and we find we get this beta is 0.11 whatever, and this is very close to the what we get from the numerics. Okay, so I'll show here, like now from the simulation and from the I mean, this comparison is perfect, right, with just the numerical solution of that uh, hydrodynamic equation. Okay, so again here we get very good agreement between numerics and here. Here the Navier-Stokes terms are not playing a role because there's no core and so on, right? So here the Euler equations are actually quite good. Okay, so I think I'll conclude. So basically, what I wanted to say is that there are two descriptions of the air in the room. One is an atomistic description and hydrodynamic description. And we asked, is this description always good? Sort of, we explored situations in kind of extreme situation. This is the blast wave in one dimension where we have an exact solution of the Euler equation. And we find that mostly there's a very good agreement between simulations and predictions from Euler. And there are some deviations which can be understood by if you include the dissipative terms. Okay, and so actually, if you look at the general solution, it's a double scaling form. In the bulk, it's Euler, and in the core, it's Navier-Stokes. Okay, there are two different scaling forms which kind of interpolate in some way. Okay, so we also have results in higher dimension. I didn't talk about that. And then I talk about this splash problem, which is like a generalized billiards problem, and where there is a very interesting separation between a hydrodynamic and non-hydrodynamic regime. But you can still make sort of nice, get some nice results from the hydrodynamic theory. Okay, and we have some conjectures for the splatter. And okay, so this I talked about. Okay, so with that, okay, so I'll just again end with this slide acknowledging people. Thanks.
Yeah. Okay. So thank you, Abhishek, for the fascinating talk. So we can take some questions because you have questions all through. So we'll try to keep it as brief as possible.
Very nice talk. So I'm a little confused about something. So if I just think in terms of dimensions, dimensional analysis.
Yeah.
So the anomalous exponent beta that you get, right?
Yeah.
Like naively, I would think that I still have the same dimension full quantities to play around with in the splash problem that I do in the blast problem, right? So which means that, yeah, so here when you have a beta which is not equal to 1,
Yeah.
that means your A is now not a dimensionless constant.
No, but this is still the same thing, right? Here I just put, oh, you're saying T to the power, I think.
Right.
Yeah. But E is still energy, right? I can put in something here to make it.
Yeah, no, I'm
you're
just
saying it's not.
Sorry.
No, you're saying there should be some other factor.
Well, no. All I'm saying is that you have something with the dimensions of energy, something
Right, yeah.
with the dimensions of density,
Yeah.
and you have time, and you're trying to get a distance.
Right. Yeah.
So in the first case, you do dimensional analysis, and you see that A is a dimensionless constant.
Yeah, I'll get
because
this,
the exponent
right,
is a third.
Yeah.
Right. I mean,
Yeah,
or
yeah,
rather 2/3.
Right. Yeah.
In the second case, because you have an anomalous exponent, beta not equal. Sorry, is not equal to 0. It's something else.
Yeah.
That means that your A, which is sitting in the denominator, is now not dimensionless anymore.
No, I think it's still.
You have to reduce some objects during some time.
Yeah.
So that your EF
Exactly.
minus beta
Right. Yeah.
can be written as initial energy into P by tau.
Right. Yeah. Yeah. Yeah.
Minus beta.
Yeah, but
Right,
what
yeah.
is that?
Some ultraviolet.
Yeah, so you have to have something which
Yeah.
is giving you the anomalous dimension.
Right. Yeah. You can put in. Yeah. You need an.
Initial speed divided the particle size.
Well, I think it's probably the separation between the little m in the big M, right? I mean, that's the only thing that I can think of which could give you this anomalous dimension, because you don't have anything else in the problem.
Yeah, I think we point.
Yes.
Uh,
Anyway.
yeah, but this I think we had some discussion on this. Like I have to think and I can. Yeah.
So yeah, you go first.
I might have missed something. Generally, for similarity or self-similar solution, all the variables have similar scaling. In the sense, velocity, any velocity like
Yeah.
matter velocity, sound speed will have generally similar scaling,
Right. Yeah.
either with r or at time.
Yeah.
Now, that means Mach number will have now. Mach number is a number, not variable in that case.
Okay.
Now, when we are talking about shock, maybe I missed some of the slides, the expression. When we talk about shock, generally, when we think of shock, typically idea is that matter was subsonic, then becomes supersonic, then it forms a shock, Rankine condition is satisfied, and shock forms. But then how this variation of Mach number will take place in your case when sound speed and matter velocity both will have same scaling. When you are pure numerical solution, I understand, but when you are with pure self-similar or similarity solution,
Yeah.
how are you getting shock? I mean, formation of the shock and Rankine condition, which is not always satisfied.
No, why do you say it's not always here?
Because
See, all the fields have the same scaling. That is
yes,
true.
so
And,
Mach
this-
number is constant, then no, because
Uh,
t to the power alpha c. Any velocity will have t to the power alpha. Coefficient will be different, of course. Sound speed will have some coefficient. Matter speed will have different coefficient.
Yeah. Right. Yeah.
No, but you are not having incompressible motion.
No, but it is the ambient medium is at 0 temperature, so there's no sound there.
Then how?
So that's why we are
how
getting.
are you
Otherwise,
defining
if
shock?
it was a finite temperature, then you would get a ballistic front. I mean, then you'd get a at whatever speed. I mean,
Then when you define, say, Rankine-Hughes condition is corresponding to some conservation of energy,
Yeah,
conservation
yeah,
of
yeah,
the boundary.
right? Yeah.
But then how if it is yeah, so how are you?
Yeah, even if it's not, it need not be at a linear like ballistic motion. The front can be. You can still get the Rankine-Hughes.
I'll think.
Right. Yeah.
So all your 1D cases, the masses were alternating.
Yeah.
So things will change if you have basically a random mixture of.
No, so okay. So random mixture, it won't change much, but actually, one might think it might be better, more thermalizing, but it will be worse because I will have stretches of, let's say, equal
regions
masses
where
and
only
yeah,
one kind for.
right, yeah, right, yeah. So it will be worse at thermalizing actually.
So another question, I mean, I read somewhere that recently Google DeepMind, they have done something which basically makes this correspondence between microscopics and hydrodynamic descriptions almost within reach of basically proving.
Oh, really?
So you have not seen that?
Oh, no, I didn't know. Oh, that's very interesting. Okay, but using AI.
Using AI, yes.
Oh, really? Okay. Okay. I think there's a question at the back.
Others have to hear.
have two different masses.
Yeah.
If you took the numbers of these two, like they're two conserved variables, right? N1 and N2, they're separately conserved. So,
No, but at a coarse grained level, I think.
I suppose, for example, I distribute them at different densities.
No, but because they are completely M1, M2, I mean, it's and they don't.
I know you've taken them alternate.
Yeah, if they could go through each other, then I think one can. Then that might be. And but here, I think.
She's worrying about random strings, right?
Yeah.
If it's random masses. No, even then, okay, then of course it's true, alternate, yeah. But then at the hydrodynamic.
Distinguishable particles. So, I mean, I thought there were two conserved quantities.
No, but at a coarse, once you do coarse grain, then it's a single field, right? And you can't. I don't think. Yeah. I mean, like the two fields, okay, but then they are not. Okay, they are individually conserved. That's true. Yeah. Yeah, each of them is conserved, but okay, okay, yeah.
Slightly more complicated.
Okay, I don't know if it will. Okay, if you write for two components, of course you will get this from that. If you add those, you can get. But you are saying if there's some additional, right? Yeah, that, yeah. Okay, maybe that's possible. Right? Yeah. Okay. For, yeah, yeah. Somehow I think because they're all very mixed up, it looks difficult.
Okay, last question.
I think there's one at the
Somebody,
end. Like,
the on
there's
the
one
back,
at the
that's the
back.
last question. You can continue the discussion during dinner.
The kinetic solutions and hydrodynamic solutions.
Uh, Okay, so I should say that when we started doing this work at that time, like, yeah, the whatever comparisons were there, they saw a big difference between the molecular dynamics and the hydrodynamics. More recently, okay, after that we also did the 2D thing, and yeah, and then we found there were some like, if you look at it carefully, even in higher dimensions there is agreement. Uh, okay, so in their work, I think, I mean, there in the most recent work, you'll find it agrees. Okay, so there was some, I think, actually there was some mistake. There was some minor mistake which which created a lot of yeah, disagreement. Sorry. Yeah. Right. Yeah. In the first paper, you'll see around 2017-18, there was big difference, and they were trying to understand, like, because it's probably due to like lack of. They checked various things like local thermal equilibrium and so on. Right. Yeah. But now it's clear that the 2D it works also very well, except again in the core there is a problem and so on.
Okay, good. So I think we have had fairly good discussion. So thanks again to Abhishek for the fascinating lecture.